Today, in this class, we will discuss about the cold form steel. So generally, we can divide the steel into two: hot rolled steels as well as the cold form steels. The difference between these two steel is that in the case of hot rolled steel members, the molten steel is passed through a series of rollers which are properly arranged to make a definite shape. In the case of cold form steel sections or members, initially we have a cold formed steel sheet which is having a slightly different chemical composition to that of the hot rolled steel, which facilitate easy bending of the member, and the members of any cross section like channel section, angle sections are made by bending of the steel sheets at the room temperature. It's very important. So these are the various cold formed steel sections as shown in the figure. So introduction, we have we are using cold formed steel nowadays very extensively in the building industry. The main distinguishing feature of cold formed steel is that they are forming from the thin steel sheets in the cold state. The another name of cold formed steel are light gauge steel or even thin walled steel structures. So there are basically two methods for forming or making the cold formed steel sections. One is by the rolling and the other one is by the pressing. So the fourth line is about the rolling, where a number of pairs of rolls are arranged and the steel sheet is passed through these rolls to get the required shape. We will see detail in the next coming slides. And the alternative method is called as the press breaking. And normally we will provide the galvanizing application for the cold form steel members to protect it from the corrosion. General yield strength is 280 Newton per mm square. Definitely there are different advantages of cold form steel over the hot rolled steel. The cross-sectional shapes formed to close tolerances and can be consistently repeated. That is, as these members or the sheets are very thin sheets, we can easily make it to the required cross section, and it can be repeated for very long members also. So, in a desired shape and desired length can be produced by the cold form steel, and we are providing it with pre-galvanized and pre-coated materials or metals to give attractive surface finish as well as the corrosion resistance. These structures can be joined by any method like riveting, bolting, welding, and by the adhesives. The good advantage of cold form steel is that it has got a high strength to weight ratio. So these materials or these members being very lightweight, but they are providing very high strength. And as they are light in weight, it is very easy to lift and transport and erect the cold form steel members. So these are the different cold form steel sections. This is a channel section. So just neglect this portion. Actually, okay, I'll tell you that this is actually called the stiffening. So if you neglect this one, the channel section will start from here. It will come straight to the right portion, right? So this long length or this length doesn't have any supports from the sides on comparison with the length. So this is a way of stiffening this web member. Okay. And here, as you are, if you're putting like this, it will be a flange, and normal case you will go for this portion upward. So this will be the web portion, and this is called as the Z purlin section. And these are the head sections, and we have angle section. Yeah, this was a sling. We will put it in reverse way. That means this portion at the top. So this will be the channel section with this stiffening region, and this will be the flanges, and this long will be the web. And you can use also provide back-to-back channel sections. And these are some rare shapes of cord form steel. As we told, the thinness will help to make very nestable sections. So there are generally two types of section. One is the open section, and the second one is the closed section. Open sections are actually the two ends doesn't meet in a very simple way. So uh, there are angle sections, there are channel sections, and also the head sections, and is there purlin, so many others are there. In case of closed section, we have the rectangular hollow section and the square hollow section, and even we have circular sections also, which have a complete closed shape, which is the meaning of closed sections. So the regarding the method of forming the cold form steel, uh, we discussed that we have a steel sheet. The steel sheet is passed through a set of rollers which are properly arranged, and at the end we will get a required cross section. Here, the figure shows how the channel sections are made from the cold formed steel sheets. So these figures, small figures, shows the um, location wise changes happens to the cold form steel sheet. So this steel sheet is made to pass through a series of rollers which will deform its shape to the finished product. It's called as a roll forming, where we have a series of rollers. The this shows a real picture of roll forming. This is actually the roof sheets which we use even for the houses and the shops. This is a real picture from the industry of how the rolling or roll forming of cold form steel shapes are done. Next is the press breaking, and these are used only for a uh, small box. It means for a very lesser number of sections, and for um, small box we go for the press breaking, where the steel shapes are formed by pressing the steel sheet. That means for making the angle section, you will first place the steel sheet like this, and by keeping a roller die here, which prevents the movement of the this portion, you will apply some pressure to the other portion to make it into an angle section. So the pressure is applied at subsequent steps to form the different cross sections. So if we again apply one more pressure at a particular point here, it can be bent to a channel section. So that is about the pressing of the cold form steel. And an important thing to note is that the properties will change. That is, upon making the cold form steel sections like this, the initial steel sheet is having a different stress strain curve, as well as the yield stress and the ultimate stress. But on folding this corner region, the formed sections, formed members will be having a different yield stress and the ultimate stress. It is shown here that the strip, it is the virgin one, and the flats are these portions after the formation, after the pressing, and these are the corners, this portion. So all will be having a different properties. The especially the yield strength between the flats are same, but the ultimate stress differs. And for the corner section, it is having a very high yield stress. The next important topic to discuss is the stiffened and unstiffened elements. So we just referred this uh, topic or this name here in this channel section at this point. We told this is actually the stiffening, right? Yeah, coming back. There are two types of elements. One is called as a stiffened element, and one is called as an unstiffened element. There are one more classification of intermittently stiffened element. I'll show you the photograph first to make it clear. Yeah. So this is an example of a stiffened element, and this is the unstiffened element. So it's not about all cross section. You can see this portion. Yeah, this portion is a flange of this beam, and this flange is supported on the other side. So this both the sides it is having a support. So this element is a stiffened element. Here, if you see this web portion alone, it is supported by this flange, but on the other side there is no attachment. So this is actually a unstiffened element. So even if one side is not stiffened, it's called as the unstiffened element. Then we have the intermediate stiffener. So we just discussed that as the length is very more or if length is very high, you need to provide a stiffener to increase the capacity and also to minimize the deflections. So here, this member is having a proper stiffening on the left side. On the right side is having a temporary, not temporary, but a made stiffener which is not fully effective, so called the intermittently stiffened element. And in this channel section, these portions are called as the edge stiffened element. So the reason to that is for this portion, the left side is having a good stiffening, right? But on the right side, we have the lips here. So it all depends on the length as well as the size of the lips. Uh, Consider whether the stiffening given to this flange is proper. So these are called as the edge stiffened lips, which is having a stiffening on the edges at one point. And one more input to use that there should be a minimal length on the lips to make sure that the flange is properly stiffened. So coming to the definitions, a stiffened element is an element which is supported by webs along both its longitudinal edges. We have seen that. Unstiffened element is supported along one longitudinal edge only with other parallel edge being free to display. So only one side is supported for unstiffened. And for intermittently stiffened element, it is made of a very wide thin element divided into two or more narrow sub-elements like this. And by the introduction of the intermediate stiffness formed during the rolling. And another important theory part is the flat width ratio. So you have an angle section, you have a hat section, you have the U sections here, and the flat width ratio is the ratio between width to the thickness of a single flat element, and the flat width W is exclusive of the edge fillets to the thickness T. So the thickness will be a constant value for any cross section. The width is something which is varying and has to be taken care. So for this section, the width of this element is from here to here, excluding this corner. So this is the edge fillet. So width W by T will be the flat width ratio for this angle. So if the angle is symmetric, then it will be having a same flat width ratio. If it is unsymmetric, it will be having two flat width ratio, out of which the highest to be considered, because highest will be always weak of because of because of the larger unsupported length. Okay, small W by T will be always safe, or it will be more stiffened or more strong. And here for the head section, we are exploding these two corners, and this will be the width of the flat, and W by T will be the flat width ratio. And so for the U sections, uh, yeah, for this member, you have from here to here, and W2, W1 are shown here, and the highest to be taken for the design. There are chances of the torsion and point symmetric sections. The torsional flexural buckling is all about the rotation of the cross section. It's a mode of buckling in which the compression members can bend and twist simultaneously. So yeah, so you have a uh, section like this. So this torsional flexural buckling means if from the suppose this is a channel section. Consider this as a channel section. Okay, take this section alone. You have the section like this, channel section, and when you see like this, that is the in the top view, this will having a total bend like this, uh, flexural buckling as well as a twisting of the cross section. That means this cross section will twist with respect to the bottom. So those are called as the torsional flexural buckling. And there are some symmetric sections like the Z section, which is having a point of symmetry. So next is about the local buckling, and the local buckling is a very important phenomenon in the case of hard form steel. So consider a flat plate like this, which is supported on all edges. So all the edges, the plate is supported, it is simply supported, and loaded in compression with will buckle at an elastic critical stress given by. So it is loaded in compression. Okay, you are applying a compressive force from the one side, and the stress is given by k into pi square e by 12 into 1 minus mu square into t by b square, where k is the constant which depends on support conditions. Pi e 12 1 like nu is the Poisson's ratio, and t is the thickness of the plate, and b is the width of the plate. So every terms is known to you now, and you can find the elastic critical stress. So this shows the theory portions, and the first one is the axially compressed plate simply supported on all the edges, and second one is axially compressed plate with one edge supported and another edge free to move. So we have the plate here, we supported at all the edges, simply supported, and we are applying a compressive stress in both the directions, and the plate will buckle like this as I am moving with the same curves which is shown on the figure. And this is about this is supported, and this set is free to move. So there will be uplift on the uh, free edge. And how to prevent local buckling? So we just seen the case of a flat plate, and when it comes to the channel section, local buckling, we have the channel section like this, and upon the application of compressive stress onto this channel plate. This will be treated as the individual plate. Okay, this rounded portion will be similar to this plate, and upon the application of the compression load, these members, this is like the case, two. There is one is simply supported, and one edge is free to move. So we have one edge supported and one edge free to move, and this will be having a mod shape, not mod shape, deformed shape like this, and this unstiffened element with an edge free to move. This is the internal element, and we need to provide the lips as we discussed in the previous slides, like here. So we need to provide the lips to provide the edge stiffening, so to avoid the local buckling at this element, this plate. So this same section with the stiffened outstands. So this technique is used for stiffening the element. So basically we are stiffening the uh, element on both sides to make it a stiffened one. So as we don't have a lips here, we provide a lips to make the section stiffened. And there is a term called the effective width method, which we have discussed before. And please note that when the channel section is applied with the compressive stresses, the for considering this element, this big plate, these are edge stiffened. Like there is stiffening on the both the edges. So when it's compressed, the stress will be highly concentrated near the edges, and when it comes to the middle of the plate, it will be lower stressed. So for calculations, for effective width, for finding the for designing the column or even the beam, we are taking only the effective width. Okay, so we are actually neglecting the internal uh, low stressed portion. So this effective width is actually the width uh, over which the member is highly stressed. We will skip these things. So these are the it's an add-on informations. There are different uh, buckling modes for the colform steel beams, like the local buckling. If you see here, this is the initial member, and this all the buckling is happening within the element. So the total cross section is not changed, but this member is buckling with respect to its original axis, right? And in the case of distortional buckling, there is a change of shape. So the member initially was like this, it is distorted to this shape. And in the case of lateral torsional buckling, which we discussed before, not before, because before we discussed flexural torsional buckling, which is a phenomenon exhibited by the column, and this lateral torsional buckling is exhibited by the beams. So there will be from the initial configuration, there will be a bending as well as the torsion behavior for these steel members. So we will wind up for today.